Assalamu alaikum, everybody. As I expected, I did not. Many students are missing. But anyway, you have the permission 5 minutes before the registration starts if you want to leave and so on, because I have to deliver the lecture anyway, but you can do that. Okay? I wanted to retract a little bit because there was a little bit of confusion yesterday. Technology did not work and so on. Okay, and also remember. So let me retract a little. So we said if we have an alternating AC source, so this we can model it with delta V, which is delta V max sine omega t. So it's a sine function. It's positive part of the cycle, negative part of the cycle. Okay, and we define that omega is 2 pi f. This is the angular frequency in radians per second. The frequency is in hertz or per second, and the frequency is 1 over the period t. Okay, and we said this is how we can get this by having a loop rotating in a magnetic field, and the mechanical rotation can be converted due to the flux change through the loop. We can get an induced EMF, and hence we can get a voltage varying sinusoid. Okay, we started with a resistive circuit. Okay, and we found that the delta V in this case of the resistor, if you measure it in such a way that you connect the same polarity of your voltmeter, so you connect it across the source, you measure the same thing. It's equal R times IR, and IR is I max sine omega t. I max is given by delta V max divided by R. Okay, so this is the if you have a purely resistive circuit, so the current and the voltage are in phase. Okay, the current and voltage are in phase. Okay, and we said we can represent this with the phasor diagram. The phasor diagram, you represent the signal by a vector that is rotating in the counterclockwise direction at an angular frequency omega, and the length of the vector is equal to the amplitude, which is in this case I max for the current or delta V max for the voltage. Okay, so far no problem. Okay, all right. Remember, we also defined the average power, and we said the average power, in order to determine the average power, we need either to determine the RMS current or the RMS voltage. RMS is root mean square, meaning it's the square root of the average of the square. So if we have, for example, the current, and the current is a sinusoidal function, if we take the square of that, so that's sine squared, the average of sine squared is 1/2. Okay, so we obtain that the average of I squared is equal to I max over 2. Okay, and I max squared we said here, so this is I max squared over 2. So here squared, so we'll write it here, I max squared over 2, and hence the RMS value is just equal to I max. So you take the square root of this, you get I max divided by square root of 2, which is 0.707 I max, the maximum current. So the RMS current is less than the maximum. Same thing, RMS voltage is less, it's 0.707 the maximum. And now we can determine the average power. It's just equal R times I RMS squared, or delta V RMS squared divided by R, or you can multiply I RMS and delta V RMS to get the average power. All right? So far, so good. Okay? This is where we had a little bit of confusion. Okay? We said delta V, which is the voltage across the inductor, is minus L di dt. And later on, we said in some other example, L di dt. Okay? So actually, I use examples from different books. So in one of the books, Survey, VL is minus L di dt, and I think that's the. But in another book, which is Holiday and Resnick, let me show you they use a different convention. So survey, your textbook, okay, he uses VL is LDIDT. Where is it? Yes. Okay, so you can see here that VL is minus LDIDT. Okay, using Lanz's law, we know the induced EMF opposes the change in the current. Okay, but in some other textbooks, like for example Holiday and Resnick, okay, he uses VL is equal to LDIDT, even though he says the induced EMF is minus LDIDT, but he uses this. The reason is when they measure they just switch the polarity. Okay? You know, if you have a battery, a 3-volt battery, for example, and you bring a voltmeter, if you connect it in one way, you read 3 volts. If you reverse the leads, you read minus 3 volts. So you can connect it 2 ways. So in some books, they use a certain convention, and in some other books, they use a different convention. That's why there is a difference between Holiday and Resnick. So he uses Holiday and Resnick uses LDIDT instead of minus LDIDT. So I wanted to make sure that I clarify that, because I had some examples, and that's why I eliminated them actually. I had some examples from Holiday and Resnick where the convention is rotated. In order to clarify that, I added this figure. Okay? So, according to survey, this is how we are measuring. So, the voltmeter is connected to the inductor, with the negative terminal connected here, and the positive terminal connected here. So, that, with this convention, then the voltage across the inductor is minus LDIT. If you reverse this polarity, so it's this VL minus V back, VL minus V back is minus LDIT. If you invert the polarity, it becomes LDIT. So this is the, I thought this figure which really makes things very clear. Okay? So, واضح, clear? So this is why we had, so in some books they use one convention, in some other books they use another convention. So let's stick with survey convention, which is that we're measuring. So when we measure the voltage across the EMF, we bring this black here and the red here. So we measure, for example, the voltage here. Then we move here and we measure the voltage here. Okay. In some books they say, okay, why you switch polarity? So since you already have your voltmeter here, your negative here and the positive here, you won't change it. You're measuring the voltage across the inductor is the same as the voltage across the source. So it is there is no standard way, I guess. Okay. Now that's why I had a problem with this figure. Okay? So remember yesterday I said let's switch it. Okay. Now this phasor diagram is actually the different convention from survey. So normally you should have this flipped. This here proof is flipped. That's why I have written it not delta VL. This is delta V of the EMF. This is the voltage across the EMF. Because if you switch the polarity, then this will be a minus sign. So it's delta V max sine omega t, which is the voltage at the source. Voila. That's why there was it. Okay. So, well, let's use survey convention. It's delta VL is that minus LDIDT. Okay, and unfortunately, you should have flipped this one. You should have flipped this one. But, so he's using the same figure as other textbooks, but he should have flipped this one because in this case, delta VL is minus. So in this case. In the survey's case, let's see here. So clearly, here delta VL is minus delta V, which is at the source. Okay. Some other textbooks they use delta VL. They use is equal delta V because they don't switch the polarity of the way they determine the voltage. So let's stick with this convention, all right? But the phasor diagram in this case, in survey, is wrong because this is really delta V. It's delta V max sine omega t, because you can see this is a sine function. Okay, and while he should have used minus, he should have been delta VL. Delta VL should be minus this one. So that's why I put here delta V, not delta VL. Okay, so I know he. This is actually a mistake from survey part. He should have used the phasor diagram that is different. Since he used a different convention from other textbooks, yet when he drew the phasor diagram, he used the same phasor diagram. I don't know if he's alive or not, but if send him an email to correct that. Okay, so for an inductor, the inductive reactance we said is omega L, and in some textbooks they call it the impedance. And we found since the current, so after we have written the loop equation, we deduced that the current through the inductor is delta V max divided by omega L sine omega t minus pi over 2. So the phase difference from the source voltage is minus pi over 2. Okay, and so we defined, since XL is omega L, we can write that I max, this is the maximum current, is equal delta V max over XL, and we can also write I RMS is also equal delta V RMS divided by XL, or omega L. So you can say, in electrical engineering, omega L plays the role of R. You know, V is equal Ri. In this case, we can say that the delta V is XL, delta V max is XL times I max. All right? Okay. So let's proceed. So I wanted to make sure we clarify that before we proceed. Okay, I think. Okay, so yesterday I think we finished this one, this example, but let's do it again. All right, so here we have a purely inductive AC circuit with an inductance of 25 millihenry and an RMS voltage of 150 volts. So V RMS is 150 volts and the inductor is 25 millihenry. Calculate the inductive reactance. Inductive reactance XL. In some books they call it the impedance. It's equal to omega L. So this is going to be equal, since we have the frequency, omega is 2 pi F times L. So this is going to be 2 pi times 60 times the inductance, which is 25 millihenries, 25 10 to the minus 3. Okay, so this is calculate the inductive reactance and the RMS current. So I RMS, we can say it's, or we can use, this is delta V RMS divided by XL, which is the inductive reactance. So remember, we used for resistance, we used to I is delta V over R. And so now we're going to write delta V RMS divided by XL. Delta V RMS is 150 divided by XL, which is 120 pi times 25 10 minus 3. Okay, so we find the IRMS. The next question, if the frequency increases from 60 hertz to 6,000 hertz, okay, so what happens to the RMS current? So IRMS2 is going to be now delta V RMS divided by the new XL, so let me call it XL2. So it's going to be 150 volts divided, instead of 120 pi, 2 pi F. So this is 12,000 hertz times pi times the inductance, which is 25 millihenries, 25 10 minus 3. So let's look at the values in this case. So you can see that in the XL is equal 9.42 ohms, IRMS is equal 15.9 amps. If we change the frequency from 60 hertz to 6000 hertz, omega will change obviously. So XL becomes, instead of 9.42, it becomes 942 ohms. It's like a much larger resistance. Okay, and you can see the current now, IRMS, is much lower. So because the inductor has a much larger reactance, it's how many times? 1,000 times? Yes, 100 times. Okay, so 100 times the reactance, that means the current will be 100 times smaller than the current in the first case. Okay, so now let's move to the next part. We're going to speak about capacitances now. Yes? Okay, just a second. Okay, so this is the one. Let's see next. Yes. So it's 6 10 to the power 3, 6 kilohertz. Thank you. Is the result correct? Still correct? So check it. Yeah. Huh? No, I mean, so the XL is 2 pi times 6,000 times 25 10 to the minus 3. صح, huh? Okay, good. You're awake. Okay? After last night. Okay, so capacitor circuit. So now we are going to have a capacitive circuit instead of an inductor, and we're going to do the same thing. We're going to write the loop equation, okay, for this capacitor circuit. And now notice I put the minus and plus to indicate where we are measuring, so that there is no confusion. Okay, so in this case, the potential across the EMF plus the potential, the sum of the voltages across the loop is equal to 0, and the voltage across the capacitor is minus Q over C. Okay, so minus Q over C. Actually, yeah, so, all right. So in this case, yeah, so actually, yeah, I should have reversed this. Okay, so then we know that the charge is equal, in this case, if we solve for Q, we get the charge is equal C times delta V. So Q is equal C delta V, and we obtain, so Q is C delta V, and since delta V is delta V max sine omega t, we obtain Q, the charge across the capacitor, is C delta V max sine omega t. Okay, now if we want to determine the current, we know there is a relationship between the current and the charge. I is just dq dt. Okay, so if you take the derivative of the charge across the capacitor, this is what you get. The derivative of sine omega t is cosine omega t. So you obtain omega c times delta V max times cosine omega t. All right. and we will use a trigonometric function. We know cosine omega t, cosine theta is equal cosine sine theta plus pi over 2. So you can verify this. This is a unit circle. Okay, if this is theta, this is theta, this is cosine theta. If you take theta plus pi over 2, you will get something like here. So this is theta plus pi over 2. The sine of theta, this is sine of theta plus pi over 2. You can see that they are equal. Okay, cosine omega t is equal sine omega t plus pi over 2. So now we can write the current as a sine function. It's omega c times delta V max times sine omega t plus pi over 2. So notice for the inductor, we used to have sine omega t minus pi over 2. For the capacitor, it's sine omega t plus pi over 2. Obviously, there is a difference here. Okay? And we can actually write this as delta V max divided by 1 over omega c sine omega t plus pi over 2. And this is what we call the capacitive reactance. Capacitive reactance XC is 1 over omega c. Remember XL was omega L. XL for inductance is omega L. The reactance for a capacitor is 1 over omega c. All right? So we can see that the capacitor current is pi over 2, 90 degrees out of phase with the voltage, delta V. And now we can see this in a phasor diagram. All right, so pi over 2 corresponds to 1/4 of a period, t. All right, and so now again, this is really delta V, not delta V of the capacitor. This is the delta V. So according to the convention that he took. All right. Okay, so this is the voltage. The voltage is now lagging, or the current is 90, or the current is leading, I guess. In this case, the voltage of the voltage source. And if we represent them in phasor diagram, remember before we had IL here, IL max. Now it's different. So this is now the phasor diagram. You can see that there is a difference of pi over 2. But as this is rotating with an angular frequency omega, also this one is rotating. The current is always leading the voltage source by pi over 2 or 90 degrees. Okay. So this is our capacitive reactance. So we can rewrite I max. This is I max here. This is I max, the maximum amplitude of the current across the capacitor is equal omega c delta V max, or we can write it delta V max divided by 1 over omega c, and 1 over omega c is the capacitive reactance. Okay, so the capacitive reactance, or in some books they call it the impedance, is 1 over omega c. All right. So now we can use so for a resistor, V max is equal R I max. For an inductor, V max is equal omega L, which is times I max. For a capacitor, V max is 1 over omega C I max. So the impedance for a resistor is R. The impedance for an inductor is omega L, and the impedance for a capacitor is 1 over omega C. Okay, so this is a convenient way of remembering these things. So we can also write the same equation for I RMS is equal delta V RMS divided by the capacitive reactance, which is 1 over omega C. Okay, the instantaneous voltage across the capacitor can be expressed. Okay, so this is now delta V is across the capacitor is delta V max sine omega t, which is I max the times the capacitance reactance times sine omega t. So he kind of reverted to the other convention in this part. Okay, the capacitor voltage amplitude and capacitor current amplitude are always related by inductive reactance, and so delta V of the capacitor is equal XC, which is 1 over omega C times IC for the capacitance. So it can be RMS or maximum voltage and current. Okay, so let's summarize. The voltage amplitude delta V and current amplitude I in an AC circuit are always related by the reactance X, or sometimes called the impedance Z. Okay, so for a resistor, the impedance or the is R, so delta V is XR times IC. For an inductor, it's omega L, delta VL is equal XL times IL, and for a capacitance, the reactive or capacitive reactance is 1 over omega C, and you can get the same equation. So here, these are the only difference is in these. Okay, and this is very convenient. So we will see when we solve some problems. So the impedance of a purely resistive circuit is R, that of a purely capacitive circuit is 1 over omega C, and that of a purely inductive circuit is omega L. Okay, now let's try to use this knowledge and answer the following question. Consider an AC circuit in the figure. The frequency of the AC source is adjusted, and so this is delta V max sine omega t. So what we can adjust the frequency, so we can adjust omega. Okay, while its voltage amplitude is held constant, so we keep this is delta V. We keep the amplitude constant and we change just the frequency. When does the light bulb glow the brightest? When is this glowing the brightest? Okay, is it at high frequency or at low frequency, or it's independent of the frequencies? So think about it for 20 seconds. So when we change this, we increase it or decrease it. When will the light bulb give us the brightest light? When the frequency is high or when the frequency is low? That's the question. All right, so think about it. Okay, ready? All right, who says A? It glows the brightest at high frequencies. Okay, all right. Who says B? It glows the brightest at low frequencies. Who says C? All right, let's figure this out. Okay, so what is the impedance or the reactance of the capacitor? It's 1 over omega C. Okay, so when omega is high, what happens to 1 over omega C? 1 over omega C is going to be low. When we have a high frequency, the reactance or the impedance of the capacitor is going to be low. When the impedance is low, will the current will be highest or lowest? Highest. So we have the impedance. So the impedance is low. So lower impedance. That means we have higher current amplitude, we should say. And since we have higher current amplitude, the lamp will be glowing brighter. Okay. So if this was an inductor, if we did this for an inductor, so the light bulb, and instead of we had an inductor, and an AC source, the opposite will happen, because the impedance of inductor is omega L. When omega is high, omega L is high. That means the impedance of the inductor is higher, or the reactance. That's or we call it reactance or impedance. When we have higher reactance, so the resistance is not changing, but now the inductor has a higher impedance, so the current will be lower. Current will be lower, and hence the amplitude of the current will be lower, and hence this will be lower brightness. Okay, so this will be the opposite if we had an inductor instead of a capacitor. Okay, so for high frequency, the reactance of the capacitor is small, so the current is large, and the lamp grows brightest. Okay, now here is another example. So now we have a capacitor connected in parallel with the light bulb and an inductor. And the question is, same question, when does the light bulb grow the brightest? When the frequency is high, when the frequency is low, or it's the same? So I'll give you half a minute to think about this. Think about reactance or impedance. What's happening to impedance and how does it affect the current? Ready? Or not ready? 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 Raise your hand if you're ready. Huh? Okay, all right. Who says A? It glows the brightest at high frequencies. Who says B? Oh, number B, yeah? Who says doesn't make a difference? C? 3. Okay, all right. So let's do some reasoning here. Okay, so we know the impedance or the reactance of the capacitor is 1 over omega C, and that for an inductor it's omega L. All right, so what happens if omega is large? If omega is large, the impedance of this part of, or this branch is going to be high. And it's going to be, so omega is high, so 1 over omega C is going to be low. 1 over omega C is going to be low, so 1 omega is low, and omega L is going to be high. So where will the current flow? Will it be flowing here or here? Most of the current will be flowing through the low resistance. It's like water, and the current will flow most through the path of least resistance. So since omega is high, 1 over omega C is low, so most of the current will flow in this branch, because the other branch has a high impedance, has a reactance that's omega L, which is large. So very little current will flow through that branch. So little current, so here let me call this I of the lamp. So in this case, I of the lamp will be lower, and the brightness will be low. Let's take the opposite. Let's say omega is low. So when omega is low, 1 over omega C becomes high. So 1 over omega C, the capacitive reactance is high. Yet for omega L is going to be low. So that means this branch, the top branch, has much less resistance than the capacitive branch. So most of the current will flow through that branch. So in this case, we can say, so in this case, IL is going to be higher, and the lamp will. So the correct answer is it will glow the brightest at lower frequencies. At lower frequencies. All right. واضح? Clear? So think about it. It's like very similar to resistance, except now for the inductor it's omega L reactance. So as omega increases, the inductance, the impedance increases. Okay, and for the capacitor it's 1 over omega C. As omega increases, 1 over omega C goes down. The impedance goes down. All right. So this is the explanation here. Okay, so here we have 8 microfarad capacitor is connected to terminals of a 60 Hertz AC source whose RMS voltage is 150 volts. Okay, find the capacitive reactance and the RMS current in the circuit. Okay, so the first question is simple. XC is 1 over omega C, which is 1 over 2 pi F times C. So this is going to be 1 over 2 pi. The frequency is 60 Hertz times 60, so 120 pi, and times C, which is 8 10 minus 6. So this and the result will be in ohms. Okay, now we can determine what is the RMS current, because we are given the RMS voltage. So V RMS is given, it's 150 volts, and we can write I RMS is delta V RMS divided by XC, which is V delta V RMS, delta V RMS divided by 1 over omega C. Okay, so let's look at the values. Okay, so the inductive, the capacitive reactance, 1 over omega C is now 332 ohms. And I RMS is equal 150 divided by 332 ohms, which is 0.452 amps. Okay? All right. So, I will let you go through this because this is optional part. This is the principle of a transformer. And I thought this is an important circuit to cover, but I want to solve a couple of problems before you go for registration. Okay, so in show, and I promise I will finish. So let's do some simple problems. Okay, so this is a Kahoot, and let me start it. And play. So we finished the chapter. It's only 4 sections. This is not a long chapter. So join the Kahoot, and again, we'll solve some problems. If you want to leave at any time, you're free, or if you want to do something else, it's okay, because I know you want to register, and the registration starts at 12, but solving some problems is nice too. Okay? So let me start with the first problem. All right. So answer question B. So this is a nice problem. A certain light bulb is rated 60 watts when operating at an RMS voltage of 120 volts. What is the peak voltage applied across the bulb? And what is the resistance of the bulb? So answer question B. نعم سمعتك the pin. It's 780-3050. 780-3050. Ready? Anybody? Ready? Raise your hand if you're ready. Your minds are not. Okay, so let me start the Kahoot. Okay, all right, so, all right, let's see. So we have 3 correct answers. Okay, so here we're given the rating of the, so the rating is the power, which is usually an average power, 60 watts, okay, and the RMS voltage, delta V RMS, is 120 volts, okay. What is the peak voltage? We have an equation that relates delta V max. Remember, delta V RMS is delta V max divided by square root of 2. So we can write delta V max is square root of 2 times delta V RMS. So that's 0.7, square root of 2 times 120 volts. Okay, this is question A. Okay, and this is what is the peak? Yeah, this is the peak voltage. The next question: what is the resistance of the bulb? Okay, so they give us the average power. Okay, and remember the average power is given by delta V RMS squared divided by R. So remember, power is Ri squared, V squared over R, or R times I. But for the average, we have to use the RMS values. Okay, so we can get the resistance R is just delta V RMS squared divided by the average power. Okay, so R in this case it will be square root of 2 times 120 divided by the average power, which is 60. So that's 2 times square root of 2. Okay, and okay, so 2 times square root of 2. Sorry, we forgot the square. So here 100 squared, square root of 2, delta V RMS squared, divided by 60. So this will be, anyway, let's go to see the values here. So you can see that the average or the resistance is going to be 240 ohms. Okay, the next question, so 240 ohms. Does the 100 watt bulb have greater or less resistance than the 60 watt bulb? Let's do it. So for R2, R2, it's going to be the same delta V RMS squared divided by the average power, but instead of average power of 60, it's going to be 100 watts. So you can see that it's going to be smaller, and in fact, when we plug the values, you find that this is going to be 144 ohms. So 144 ohms, which is less than R1. Let's call this R1. Okay? All right. The current in the circuit shown equals 60% of the peak current at t equals 7 milliseconds. What is the lowest source frequency that gives this current? Okay, we have an equation for the current, D. Okay, we know I is equal I max sine omega t. Okay, and all right, so this is going to be equal to 60% of the peak current. So this is going to be 0.6 I max, meaning sine omega t is going to be 0.6. Okay, now so what is omega t? So omega t is going to be the inverse sine of 0.6. Okay, and you have to be careful. You have to do this in radians. It's so you should find the value in radians, not in degrees, and you can solve for t. Okay, sorry, what is the lowest frequency? So you can solve for omega. So omega or 2 pi f. So this is omega, which is 2 pi f times t, which is 7 milliseconds, is equal to the inverse sine of 0.6, and we get f is just equal to the inverse sine of 0.6 in radians, not in degrees, divided by 2 pi t. And when you do that, you find the value that this is 14.6 hertz. Frequency is 14.6 hertz. Okay, so maybe just one more problem, and then you can go for registration. All right, so 2 minutes for this problem. Now, question, Part B, the average power is VRMS V squared over R. Okay, so R is going to be VRMS squared divided by the average power. VRMS is 120 squared divided by the average power, which is 60 watts. You find that resistance is going to be 240. Go back to what? The slide. This is the first slide. Okay, so here the first question, we know delta V RMS is delta V max divided by square root of 2. So delta V RMS is going to be square root of delta V max is square root of 2 times the so the value in this case, this is the question here. So delta V RMS times square root of 2 is going to be 169.7. Did I make a mistake here? Yeah, so sorry. So here, okay, so delta V RMS is 0.707, delta V max, so this is times 0.707, which is 1 over square root of 2. So now delta V max is going to be equal, which I should not, all right, so this is going to be delta V max, this is, we're trying to determine the peak voltage, so delta V max is delta V RMS divided by 0.707. So you find that, so this will be 169.7 volts. Part B. Okay. So what's the problem with part B? The average power is VRMS squared divided by R. No, that's different. Now, VRMS is already given here. Here with okay. So we used here P average is delta V RMS squared divided by R. For calculation, this is delta V RMS squared divided by R. So yes, so delta V RMS is going to be 120. So 120. So sorry. So this would be 120 squared divided by P average 60. So this will be. So you find that 240 ohms. Sorry, I made a mistake here. So this is 240 ohms, because the VRMS is already given. the voltage. Okay. All right. So let's go to the next problem, and I will finish with this problem, so that you can go for the registration. Okay, 2 minutes. So you just need to answer question B for this question. Okay, ready? Okay, so let's go to the next question, the answer. Okay, well, good. 4 correct and 3 incorrect. All right, so let's try to do this without making mistakes. Okay. All right, so here we have 3 light bulbs connected to 120 volt source. So this is the RMS voltage here, 120 volt. Okay, and the bulbs 1 and 2 have a power rating of 150 watts, and bulb 3 has 100 watt rating. Find the RMS current in each bulb. Okay, so right, so here P, what do we know? We know P, so P average is going to be equal I RMS times delta V RMS. Okay, so I can use since we have the power rating, so let's take for R1. For R1 we have P average 1 is equal I RMS 1 times delta V RMS, which is given, and I can get I RMS. So I RMS in this case 1 is going to be P average, which is 150 watts, divided by delta V RMS, which is 120 volts. Okay, so this is the current for 1, which is also equal to the current of 2. So this is also for 2, because they have the same power rating. However, for lamp 3, I RMS 3 is going to be 100 watts, because its rating is at 100 watts. 100 watts divided by 120 volts. Okay, now let's do the current. The current in each bulb. This is the resistance B. Okay, now we can also use the same thing. We can say P average is equal R times delta V RMS squared, and we are given delta V RMS, so I can get R is just equal the average power divided by delta V RMS squared. Delta V squared over R. It's Ri squared delta V squared over R. So this is going to be mean R is going to be equal to delta V RMS squared divided by the average power. So for R1, delta V RMS is 120 squared divided by the average power, which is 150 watts. Okay, So when you do that, you find that R1 is going to be equal to 96 ohms. So this is 96 ohms, same as R2. R3 is going to be 120 squared divided by 100 watts. And when you do that, you find that this is equal to 144 ohms. Okay, I will stop here so that you can go register, and we'll do some more problems. Have a good vacation, enjoy your Eid, and don't forget about the quiz after the Eid break. Okay.